Let's go on with our study of methods for nonlinear prediction. We are talking about piecewise polynomials. So we have seen that polynomial regression is interesting, but has some shortcomings. We have given a quick look at techniques based on step functions that are quite effective, but after all, I don't like very much showing a prediction of this type with the discontinuities, of course, and these are unavoidable. And you can use step functions also for logistic regression, of course. And now the idea is that we could do better by means of piecewise polynomials. We have seen that the basic idea of fitting a different polynomial in each region is not good, because exactly as it happens for step functions, we obtain discontinuities that are not nice to see and also difficult to justify. Therefore, we are looking at piecewise polynomials that have some continuity constraint, and the piecewise polynomials that are mostly constrained in the knots are the so-called splines. They have the maximum amount of continuity. For instance, let's think about linear splines. Here I have a piecewise linear polynomial, and I am imposing that in the knot, so where the two regions are separated, these two polynomials, the left one and the right one, are sharing the same value. And as a matter of fact, you cannot imagine that they are sharing something more. So if they had the same derivative, then you would have just a unique polynomial on all the x domain. So this is the maximum amount of continuity you can afford if you are using a piecewise linear model. Instead, if you are using a cubic piecewise model, in this case, when you are in this point, you can have the function that is continuous, its first derivative and its second derivative. Again, you cannot do much more, because if you were to impose that here also the third derivative is equal, then at that point you will have a unique polynomial. So the purpose of having a flexible method, and flexibility has to do with the fact that it's local. So here you have a polynomial that takes care of this part of the data, and here you have another polynomial that takes care of this other part of the data. And this is their power, the fact that you are splitting your original problem in more or less local problems where you can get good fits using low degree polynomials, although they cannot be completely independent as it happened here, but we like that they are consistent. And so we are looking for the maximum amount of consistency, and that is, for a linear spline you can arrive at continuity and nothing else. For a cubic spline you could ask that there is continuity of the first derivative, a continuity of the second derivative, and you cannot go any further. Okay, and but in practice, how can I solve the problem of estimating these splines? Let's start from linear splines. It happens that they can still be written in a very similar fashion as we have just done with polynomial regression. So we can represent a linear spline model just as a linear combination of many terms. Here we have the intercept, and then we have terms that we call B1 xi, B2 xi, and so on. And these bk are the so-called basis functions. So a linear spline model can be written this way. What are these basis functions? They are something very simple. So the first one is just a line. The second one is the positive part of this difference. This means that whenever xi minus xi k is less than whenever xi minus xi k is greater than 0, so this difference is positive, you get the difference. Okay, if xi is less than or equal to xi k, then you have 0. But I think it's simpler to look at the plot. So this is the basis function. So until you are less than 0.6, in this case xi k is 0.6, you are 0. But when you exceed this term, you go up as x, as the difference between xi k. In this case, xi k would be 0.6. And how does it happen that such simple basis functions can give rise to a linear spline? Well, it's not difficult to understand, because if you take the first basis function, that is xi, this is a line through the origin. Okay, remember that we also have the intercept. So after all, if we consider the intercept and the first basis function, you will just have a line, and then we are going to sum the basis function through proper coefficients to this line. And if I sum the orange function with coefficient, for instance, a negative coefficient, so I take the sum of the blue function and the orange, with the orange multiplied by negative coefficients, you will see that so far, until 0.6, there is no effect when you take the sum of these two functions. But here, if you have a negative coefficient, the effect of this basis function will be to bring down the slope of the function. So you can imagine that here there is another knot, and so here there is another function that passes from 0 to some slope. And therefore, at that point, you will have a change of slope also here. So by putting together, by summing these basis functions, you get a function that is continuous, but has changes of its slope in correspondence of the knots. Okay, this is very easy to understand for the linear spline. The cubic spline is a bit more complicated, but not that much. So again, you can write your function as a linear combination of basis functions, and here the basis functions, we already have the intercept, I remember, but the basis function b1, b2, b3 are xi squared, xi cube. Of course, here there is nothing local so far. So if I just used this basis function, this will be just a cubic polynomial. But starting from the fourth one, I'm introducing the positive part, this plus, of the cube of this difference. And this works exactly as before. So if the difference is positive, you just take the difference, okay, to the cube, to the third power. If the difference xi minus xi k is negative, you take 0. So if we look at the plot, a generic basis function looks like this. So it is 0 until I get at xi k, and after xi k, you just have this behavior, okay. This behavior because the difference xi minus xi k has become positive. Here again, xi k is equal to 0.6. And what happens when you are summing these basis functions? Well, here you have the polynomial, the cubic polynomial that is characterized by xi squared, xi cubed, each of one with each coefficients. But when you arrive here, you are summing this orange function, you will see that the orange functions will cause a deviation. The important thing is that if you look at this, you can see that the function, the first derivative, the second derivative are all equal to 0. Therefore, when you compute the sum, in the point of the sum, nothing is seen on the value, the first derivative or the second derivative, because they are all zero. So you have a very smooth transition that comes into play at this point. Okay, but how many constraints, how many unknown parameter? Well, if we look here, we can see that we have beta 0, this is one parameter, and then if we have k knots, we have to use k plus 3 basis function. So eventually we have k plus 4 basis unknown parameters, so beta 0, and then the k plus 3 parameters, beta 1, beta 2, and so on. And therefore the number of unknowns, if you are using this spline that is also called the regression spline, will be k plus 4, where k is the number of knots. However, there is also the possibility of adding extra constraints that force your spline to extrapolate as a line. So the idea is that if you take a cubic polynomial, its extrapolation will follow a third power law. But this kind of extrapolation could be really wiggly, and we don't like unstable extrapolations, and rather it would be more cautious to make a linear extrapolation. Okay, this can be forced with some constraints. So we are constraining that some derivative is 0, for instance, and in particular we need 4 extra constraints. And these are 2 constraints at the end, 2 constraints at the beginning, and this means that we obtain a spline whose number of free parameters is smaller. And the splines takes the name of natural cubic spline. And here you can see a comparison between a natural cubic spline and the cubic spline. You can see that they are doing quite similar, although the extrapolation of the cubic spline in this direction might seem a bit excessive. Okay, but most importantly, what changes are the confidence interval. So you can see that the natural cubic spline, although it diverges, it doesn't not give these such large confidence intervals in this region. Okay, fitting splines is easy if you have the package. Here reference is made to the software package R, but you can find software packages in MATLAB or Python, and so this is not going to be a problem. And these packages should be able to give you the point-wise prediction, but also the confidence intervals that we were discussing before. This is what happens for regression. This is what happens for classification. Okay, that's good. There is a problem, an important one that remains open, that is knot placement. So we have to decide the number of knots, and this is important because the number of knots decides the number of parameters to be estimated, so it's related to the flexibility of the model, but also we have to decide the number of knots. So once you have decided the number of knots, there is also the problem of placing them. So a possibility for placing the knots would be to look at the quantiles of your data. So for instance, one should not put many weights here where you don't have data because they are completely wasted, but I will concentrate the data where there are points, and I could do this by looking at the quantiles. So for instance, I should put a knot every decile of my distribution. If I had 100 of points to put and I had very many data, I could put a knot in correspondence of each percentile. But in that case, it would be a quite large model with 100 parameters. Remember that a cubic spline with k knots has k plus 4 parameters, or as as you want, call them degrees of freedom, while a natural spline, by adding the constraints of the linear extrapolation, a natural spline with k knots has just k degrees of freedom. And here you can appreciate the advantages of using natural cubic splines over polynomials in this figure, because you can see the same data, the natural cubic spline that has 15 degrees of freedom as this profile, and in most of the region it is the same as the one obtained by the 14-degree polynomial, but you can see that here the bad extrapolation properties of the polynomial clearly arise. One would never use such high order polynomial as a rule, because it could work well when you have much data to block all strange oscillations, but when you don't have enough data, then you will have strange behaviors that you cannot control. Okay, I think we can stop here.